good morning students. I am Vaishagi Shah from LJ Institute of Engineering and Technology. In our subject Fluid Mechanics and Hydraulics, in last lecture we studied properties of fluid, different properties of fluids like capillarity, surface tension, viscosity, etc. So now in today's lecture we are going to solve some examples based on that property. Okay, so let's start. First, quickly revise the equation to solve the example. So first of all, surface tension, we derive the theory of surface tension on liquid droplet. Okay, and the equation for surface tension, that is P, which is pressure, P equals to 4 sigma by D. Here sigma is a surface tension and D is a diameter of liquid droplet. Okay, so this is the equation of surface tension on liquid droplet. Now the equation of surface tension in hollow bubble, that is P equals to 8 sigma by D. Equation for capillarity, that is H. Now capillarity, that is height of rise of liquid in a glass tube. So that height of rise we indicate as H, and H equals to 4 sigma cos theta by rho g d, where sigma is a surface tension, theta that is angle, rho mass density of liquid, g gravitational constant, and d is a diameter of glass tube. Okay, and the next equation, which is for viscosity, also called Newton's law of viscosity, the equation is tau equals to mu into du by dy, where tau is your shear stress, mu is a dynamic viscosity, du that is change of velocity, and dy is a change in distance. So these are the equation for different properties of fluid: surface tension, capillarity, and viscosity. Okay, so now we will solve some example based on this equation. So let's start. Our first example is the surface tension of water in contact with air is 0.0725 Newton per meter. The pressure inside the droplet of water is 0.03 Newton per centimeter square in excess of outside pressure. Calculate the diameter of water droplet. Okay, here water droplet, liquid droplet is given to you, and the surface tension sigma, which we indicate as sigma, the value of sigma is 0.0725 Newton per meter, and the pressure we indicate as P equals to 0.03 Newton per centimeter square. Here we have to find out diameter of liquid droplet. As we know the equation, pressure P equals to 4 sigma by D. Okay, here P is known to us, sigma is known to us, and the unknown is only D. So equation for D, that is D equals to 4 sigma by P. Now placing the values 4 into 0.0725 divide by pressure P. Here pressure is given into Newton per centimeter square. So convert into Newton per meter square. So that value will be 0.03 into 10 raised to 4. So your final answer for D, diameter of liquid droplet, that is 0.966 mm. Clear? Okay. Now in our lecture we studied surface tension in liquid droplet, but in example here there is one theory for hollow bubble also. As you can see here, this bubble, which is soap bubble, maybe it is a soap bubble, so that is a hollow. From inside the soap bubble is also called hollow bubble. Now surface tension in hollow bubble. Okay, so hollow bubble like soap bubble in air has two surfaces in contact with air. As you can see in the diagram, for this hollow bubble, two surfaces, first outside and second inside the bubble. Both the surfaces are in contact with air, inside and outside. Okay, so here two surfaces are subjected to surface tension. Okay, not only one surface, inside and outside, both the surfaces are subjected to surface tension. So in that case, the equation for surface tension P equals to 8 sigma by D. As we know the equation for liquid droplet, which is 4 sigma by D. Now multiply that equation with 2, because here two surfaces are in contact with air. So the final equation for hollow bubble, that is 8 sigma by D. Okay, so let's solve the example. Find the surface tension in soap bubble. Here soap bubble is given to you. That means it is the example for hollow bubble of 30 mm diameter when the inside pressure is 3.5 Newton per meter square above atmospheric pressure. So here, first of all, diameter given to you, which is 30 mm. Now convert mm into meter. So it is 30 into 10 raised to minus 3 meter, and pressure, which is P, 3.5 Newton per meter square. Now for a soap bubble, we know the equation P equals to 8 sigma by D. Now here we have to find out, sigma, that is surface tension. As we know the value of P, which is 3.5, equals to 8 sigma by 30 into 10 raised to minus 3. So making sigma as your subject, your final answer for sigma is 0.0131 Newton per meter. Okay, clear? Now next example, this example is for capillarity. Okay, calculate the capillarity rise in a glass tube of 3 mm diameter when it is immersed vertically, first in water, second in mercury. Okay, here a glass tube is given to you, and the glass tube of diameter 3 mm is immersed vertically, first case in water and second case in mercury. The tube is immersed in two liquid, first in water and second in mercury. Okay, now the surface tension of water sigma, that is 0.074 Newton per meter, and for mercury it is 0.52 Newton per meter. Okay, sigma for water and mercury is given. The specific gravity of mercury is 13.6. Angle of contact of water is 0 degree, and for mercury it is 130 degree. Now if in any example the angle of contact is not given to you, then you have to remember this value. For water theta is 0 degree, and for mercury theta is 130 degree. Okay, so now here diameter of glass tube is 3 mm, so 3 into 10 raised to minus 3 meter. For water, sigma equals to 0.074 Newton per meter, and for water specific gravity is 1. Now we have to find out capillary rise in water. So the equation for capillary rise, that H equals to 4 sigma cos theta by rho g d. Now placing the values here, 4 into 0.074 into cos theta, here theta is 0, divide by rho. density of water, which is 1000 into 9.81 into 3 into 10 raised to minus 3. So by solving this in calculator, your answer for capillary rise is 0.01 meter. Okay. Now the second case, capillarity fall in mercury. Remember that there is capillarity rise for water and capillarity fall for mercury. So the for mercury, sigma given to you is 0.52 Newton per meter, and for mercury specific gravity is 13.6. Now H, that is 4 sigma cos theta by rho g d. So 4 into 0.052, that is your sigma, and theta is 130 degree. So cos 130 divide by mass density of mercury, that is 13,600. Okay, 13,600 into 9.81 into 3 into 10 raised to minus 3. So your final answer, that is 0.00334 meter. Now here the sign is negative. Okay, the answer is in negative, which indicates there is a capillarity fall in mercury. For water, the answer always comes into positive, and for mercury, your answer always is in negative. Clear? So this is the example for capillarity. There is a capillarity rise in water and capillarity fall in mercury. Okay. Now our next example, a plate of 0.025 mm distance from fixed plate moves at a 60 centimeter per second, require a force of 3 Newton per meter square. To maintain this speed, determine the dynamic viscosity between two plates. Okay. So here first of all, two plates are given to you, top and bottom, two plates are given. Clear? Now the plate 0.025 mm distance. So distance between two plates here, as you can see, the distance between two plates is 0.025 mm. So distance between two plates we indicate as dy. Now dy is 0.025 mm, convert into meter, then it is 0.025 into 10 raised to minus 3 meter. Now here the top plate is moving and the velocity of upper plate is 60 centimeter per second. Top plate is in moving condition, okay, and the velocity is 60 centimeter per second, which is 0.6 meter per second. Here in this data given to you that bottom plate is fixed. So this is your bottom plate which is fixed. Okay. The velocity of lower plate is 0 because it is fixed. So velocity of bottom plate is 0. Now if we have to find out change in velocity, which is du, so du equals to u minus 0, velocity of top minus velocity of bottom, so u minus 0, so the change in velocity is 0.6 meter per second. Okay. Now here again this is your diagram. Now using Newton's law of viscosity, in data the force per unit area, which is tau, is 3 Newton per meter square given to you. So here tau is 3 Newton per meter square. Using Newton's law of viscosity, the equation of Newton's law, that is tau equals to mu into du by dy. Now in this equation tau is known, du is known and dy is known. Okay. So the only unknown is mu, and then mu is your dynamic viscosity, which we have to find out. So here tau, that is 3 equals to mu into 0.6 divided by 0.025 into 10 raised to minus 3. So the answer for mu is 1.25 into 10 raised to minus 4 Newton second per meter square. Remember the unit for dynamic viscosity, that is Newton second per meter square. Clear? So, this is your final answer for dynamic viscosity. Okay. Now, our next example, calculate the dynamic viscosity of an oil which is used for lubrication between a rectangular plate 1 meter by 0.4 meter and an inclined plane with angle of inclination 30 degree. The weight of plate is 600 Newton and it slides down to the inclined plane with a uniform velocity 0.35 meter per second. The thickness of oil film is 2 mm. Okay. Now, in this data, first of all, the rectangular plate is given to you and the area of rectangular plate is 1 meter into 0.4. So, the area is 0.4 meter square. So, here this is your rectangular plate 1 meter by 0.4 meter. So, area of this rectangular plate is 0.4 meter square. Now, next in data, the inclined plane is given to you and the angle of inclination is 30 degree. Okay. So, this is your inclined plane, angle of inclination is 30 degree and the rectangular plate is moving downward on this inclined plane. Okay. Here, oil is used for lubrication between plate and plane. So, here that is your plate and this is your plane. So, this is your plate, this is your oil, as you can see, this is your oil layer which is used as a lubrication between plate and plane. So, this is your oil layer. So, the thickness of oil layer is 2 mm. Now, the distance between two layers, as we know that distance between two layer, okay, or two plate is dy. So, here the distance is oil, a thickness of oil layer, that is dy. So, dy here is 2 mm. Okay. Now, the weight of this plate, the plate is moving inclined, okay, but the weight of the plate is acting in downward direction. Okay. So, the weight of the plate, as you can see, weight of the plate is acting in downward direction and the weight of the plate is W. Now, the weight is acting at angle theta. So, there are two components of weight, W sin theta, because here there is a angle theta, as you can see angle theta here. So, here due to this, this component is W sin theta and the vertical component is W cos theta. Clear? The weight is acting downward at angle theta. So, there are two components, W sin theta and W cos theta. Now, weight of plate, which is W, is given to you, that is 600 Newton, and velocity of plate U, that is 0.35 meter per second. So, velocity is 0.35 meter per second. Now, this data is given to you and by this you have to find out dynamic viscosity, which is mu. Okay. This things is given to you. Now, first of all, this is your diagram. Okay. Thickness of oil film, which is dy, that is 2 mm. Convert into meter, then it is 2 into 10 raised to minus 3 meter. And from the figure, the component which is helping the plate to moving downward, that is W sin theta. So, the component acting along the plane, that is only W sin theta. So, here the component of W is W sin theta. Here we know that weight W is 600 and sin theta, theta is 30 degree. So, your answer is 300 Newton. Now, as we know that shear stress tau equals to force upon area, we know the value of force 300. Okay, now that force F equals to W sine theta. So F equals to W sine theta, that is 300 Newton. So 300, and area of plate is 0.4 meter square. So 300 by 0.4, that is 750 Newton per meter square, which is your shear stress tau. Now, as we know that change of velocity du, that is u minus 0. Now, if we consider bottom, your inclined plane as a fixed, then du equals to u minus 0. So that u is 0.35. So ultimately du equals to 0.35. Okay. By using Newton's law of viscosity, the equation is tau equals to mu into du by dy. Tau is your shear stress, which we found by using equation F upon A. Mu, that is dynamic viscosity, which is unknown. Du, that is change of velocity, we already have the value of du, and dy here, that is thickness of oil layer, or you can see the distance between two plates. So by placing all the values here, tau equals to 750 equals to mu into 0.35 divided by 2 into 10 raised to minus 3. So by solving this equation by using calculator, your answer for mu is 7.286 Newton second per meter square. The unit for mu is Newton second per meter square. So this is your final answer for dynamic viscosity. Okay. So in today's lecture, we solve some example based on different properties of a fluid. You can solve more examples. There are so many examples given in textbook, but the refer the equation. The most important thing is equation. Okay. So by using that equation, you can solve any examples given to you. Okay. So the next remaining topics we will discuss in our next session. Goodbye.